Hello everyone, I'm Thomas and I'm excited to bring to you a brief history of the evolution of the atomic model, specifically the Bohr-Rutherford model. Before touching on the Bohr model, I think it would be beneficial to take a few steps back in time to when the idea of the atom was first conceptualized. To our knowledge, it is believed that the Greek Democritus was the first to conceive the idea of the atom, although philosophers in China and India were developing similar ideas. Using the logic that after breaking object into smaller and smaller pieces, there will eventually come a point that the object cannot be separated any further. Democritus came to this idea by breaking things such as wood and rocks, but this could be demonstrated with nearly anything from cars to textbooks to nasty vegetables. The idea is that the smallest particle left will be deemed indivisible, which is the meaning of the Greek word atomos, or what we call it today as an atom. After this early history, little development on the idea of the atom is known until about 2,000 years later with the contributions of Englishman John Dalton. John Dalton concurred with Democritus's idea that atoms are the base unit of elements, but in addition he proposed that atoms of different elements will have different masses and properties. It wasn't until J.J. Thompson's era that atoms were discovered to be composed of substructures, particularly negatively and positively charged particles, later called electrons and protons. J.J. Thompson's improvements and contributions to ongoing cathode ray experiments enabled him to verify the negative charge of electrons using magnetic and electric fields. By collecting the rays, Thompson measured an excess of negative charge, which allowed him to calculate the mass and charge of an electron. Thompson also analyzed hydrogen ions known today as protons, and discovered their mass to be approximately 1,000 times greater than that of an electron. These discoveries led to J.J. Thompson's portrayal of an atom using the plum pudding model. The chunks within the pudding represent electrons, while the remainder of the otherwise homogeneous mixture represents positively charged protons. After J.J. Thompson's findings led to the general composition of the atom, Ernest Rutherford made additional findings through his gold foil experiment. Rutherford's experiment provided the basis of the knowledge that we have today about the nucleus of an atom. Ernest Rutherford shot alpha particles at gold foil surrounded by a phosphor sheet to observe the deflection patterns of the positively charged alpha particles. The alpha particles' energies are much greater than the energies of a typical atom, such that Rutherford expected the alpha particles to pass straight through the gold foil. While many such alpha particles behaved as expected, Rutherford was startled by the occasional particles that were deflected off the gold foil by a large angle or even directly back towards the source. This phenomenon led Rutherford to discover the anatomy of the atom. He learned that the center of an atom is composed of a very dense but small positively charged nucleus relative to the large overall size of an atom. For the alpha particles that passed straight through the foil, it demonstrated that the majority of the atom is empty space. Rutherford's findings disproved J.J. Thompson's plum pudding model and gave way towards the planetary model that we are familiar with today. Rutherford's planetary model displays electrons with little mass orbiting around a higher mass nucleus, where orbital sizes vary based on the mass of an atom. Rutherford's findings inspired Niels Bohr to collaborate with him to research the atomic spectrum of hydrogen, the simplest atom. Bohr theorized that electrons revolve around the nucleus in set orbitals and that electrons cannot deviate from these orbitals. He proposed that electrons could gain or lose energy, allowing them to move from one orbital to another, but that the electrons could not exist in between orbitals. By observing the absorption and emission patterns of electrons, Bohr was able to build on the planetary nature of the atomic model, proposing that electrons could be excited by photons of light, advancing them to higher energy orbitals. Similarly, electrons on higher orbitals could emit light photons to drop down to lower, more stable energy orbitals. Bohr's research provided groundbreaking evidence to explain why different frequencies of light were needed to eject different electrons of an atom. To this point in time, Bohr's model provided the most accurate representation of the atom. While the Bohr model was key in understanding the spectrum and size of a hydrogen atom, as well as the fact that electron orbital energies are quantized, his model failed to represent multi-electron atoms accurately. Unlike the simple circular orbitals proposed by Niels Bohr, the scientists Schrödinger and Heisenberg proposed a different theory. Schrödinger and Heisenberg proposed that we cannot know the exact location and trajectory of electrons at the same time. Instead, they applied the idea that electrons exist in different electron clouds surrounding an atom. Using their knowledge of elements and their properties, they proposed that we can use probability to approximate the location and density of electrons on an atom. Rather than a set orbital, electrons exist in specific orbital clouds based on their properties as organized in Mendeleev's periodic table of elements. While the Bohr-Rutherford model is not technically the most accurate atomic model anymore, it provides valuable information about the anatomy and nature of an atom. Just as science continues to make advances in discovering reality, each of the scientists behind the evolution of atomic models made great contributions to our current understanding of atoms today. I hope you found this video insightful. Thank you for watching.